Consider the equation showing the formation of ammonia, that is N2 plus 3H2 giving 2NH3. For this particular reaction, standard enthalpy of reaction is given as minus 91.8 kilojoules per mole. Now write the reaction in the reverse order. Start with ammonia. So the new equation will be 2NH3 giving N2 plus 3H2. Now for this particular reaction, standard enthalpy of reaction is given as plus 91.8 kilojoules per mole. So here when we write the reaction in the reverse order, the sign of standard enthalpy of reaction will also get reversed. So note that the sign gets reversed. Next we shall learn about Hess's law of constant heat summation. What is the law? What is the statement? It states that if a reaction takes place in several steps, then its standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reactions into which the reaction may be divided at the same temperature. So if a reaction takes place in different steps, then the standard reaction enthalpy of the overall reaction will be the sum of the standard enthalpies of all the intermediate reactions. Now let us see how we can use Hess's law to calculate standard enthalpy of reaction. For example, consider the reaction equation C plus half O2 giving CO. How can we calculate the standard enthalpy of reaction for this particular equation, that is C plus half O2 giving CO? For that, consider the formation of carbon dioxide. The equation showing the formation of carbon dioxide can be written in two different ways. First, we can write C plus O2 giving CO2. For this particular reaction, standard enthalpy of reaction is equal to minus 393.5 kilojoules per mole. Mark this as equation number 1. The formation of carbon dioxide, the equation can also be written in another way. That is, you can start with carbon monoxide. So the equation will be CO plus half O2 giving CO2. For this particular reaction, standard enthalpy of reaction is equal to minus 283 kilojoules per mole. Mark this as equation number 2. Now write equation 2 in the reverse order. So the equation now becomes CO2 gives CO plus half O2. Now since we have written the reaction in the reverse order, for this particular reaction, standard enthalpy of reaction will also get reversed. The sign will get reversed. So for this particular reaction, standard enthalpy of reaction will be plus 283 kilojoules per mole. Mark this as equation number 3. And after that, add equations 1 and 3. That is, we have to add the equations 1 and 3. So we can write C plus O2 giving CO2 plus CO2 giving CO plus half O2. Now when we add these two equations, we get C plus O2 giving CO plus half O2. CO2 will get cancelled because one appears on the reactant side and other appears on the product side. Now half O2 can be brought to the reactant side. So we get C plus half O2 giving CO. So this is the desired equation. And to get the desired equation, we have added equations 1 and 3. So for the final equation, that is C plus half O2 giving CO, standard enthalpy of reaction can be obtained by adding the reaction enthalpies of the reaction equations 1 and 3. So we have to add minus 393.5 and 283. Now when we add these two values, we get standard enthalpy of reaction as equal to minus 110 kilojoules per mole. Standard enthalpy of combustion. It is denoted as delta H naught C. What is standard enthalpy of combustion? It is the enthalpy change accompanying the combustion of 1 mole of a substance in the standard state. For example, consider the combustion of butane. C4H10 plus 13 by 2 O2 gives 4 carbon dioxide plus 5 water. And the enthalpy of combustion is found to be minus 2658 kilojoules per mole. So this much amount of energy will be released when 1 mole of butane undergoes combustion. Next we shall consider enthalpy of atomization. It is the enthalpy change accompanying the breaking of 1 mole of bonds to obtain atoms in the gaseous phase. For example, consider hydrogen H2 gas giving 2H gas. Here the enthalpy of atomization is equal to 435 kilojoules per mole. Note that delta H naught A is positive, which shows that 435 kilojoules of energy is required to break 1 mole of bonds. Now consider sodium solid giving sodium gas. The enthalpy of atomization is given as 108.4 kilojoules per mole. Here sodium changes from solid state to gaseous state. So it actually undergoes sublimation. So here in the case of sodium, enthalpy of atomization is the same as enthalpy of sublimation. Next we shall learn about bond enthalpy, delta H naught bond enthalpy. Consider a diatomic molecule like hydrogen. Bond enthalpy is the energy required to break 1 mole of bonds of a particular type. So hydrogen H2 gas gives 2H gas. The amount of energy required to break 1 mole of HH single bond is given to be 435 kilojoules per mole. So 435 kilojoules of energy is required to break 1 mole of bonds present in hydrogen, 1 mole of hydrogen. Now for polyatomic molecules like methane CH4, we can write the equation as CH4 giving C plus 4H. And here in this case, enthalpy of atomization is given as equal to 1665 kilojoules per mole. So what will be mean bond enthalpy equal to? It will be equal to 1665 divided by 4, which is equal to 416 kilojoules per mole.